good afternoon or good morning, depending on the time zone that you are in watching this presentation. First to say that it's my real pleasure to be here to present this subject. I was originally planning to be in person, but due to travel complications, I'm presenting this virtually. In any way, I want to thank the organizers of the Data and AI Summit for their flexibility, and again, it is real my pleasure to be able to talk about the subject. So, my name is Edon Begoli, and I'm gonna tell you in a second about my background, but the topic of my presentation is general introduction to the adversarial AI, and specifically we'll talk about the nature of the threat, what it is, how it manifests itself, what are the possible impacts, and then some mitigation strategies. This is intended as a 45 minutes session, so this is of course is going to limit to a degree how much can we cover it, and this is not a small field, but either way, this is going to be, again, it's my pleasure to be able to cover the subject, and I'll do my best that we go through as many of the subjects as possible. So first, who I am. I lead a research section at Oak Ridge National Lab, and I serve there as a distinguished member of the research staff. And I will tell you in the next slide, what is Oak Ridge National Lab? If you don't know, if you kind of want to Google it quickly and learn more about it, the most important news from the last week is that we are the host of the first exascale computer at that scale. So the United States is again at the forefront of leadership in high-performance computing, and this is what we're known for. And many of us have attached backgrounds because that brings together, lots of resources and problems, and certainly talented people to work on related problems. I'm a computer scientist in terms of my background, and in addition to being a member of the research staff at Oak Ridge National Lab, I also teach as a joint faculty at the University of Tennessee, Knoxville, and I'm a visiting scientist appointment with University of California, Berkeley, Skylab. Most importantly, I'm actively pursuing research in robust and reliable analytic decision-making as a whole, because in this domain we try not to focus on buzzwordy things such as, sometimes people question like, what is AI, what's ML, which came first, which one leads us to the general artificial intelligence, and how far it's going to be. Well, in my space, we are really looking at supporting analytic decision-making in various different federal and research domains, and how do we make that decision-making, which is largely enabled by computing, robust and reliable. In other words, to what degree can we trust decisions that we are making, and what are the limitations of that trust. So that's my very generically stated background. The most important thing probably to say is that I'm actively involved in the area that I'm presenting today. So this is some of those topics, even though they are really presented as a survey to you all, are based on the research and practical experience. So briefly about Oak Ridge National Lab. Oak Ridge National Lab came out of Manhattan Complex, just like Los Alamos and Argonne National Laboratory and PNNL. So this is how the Oak RNL looked like in 1943. It was in the middle of Tennessee hills. There was nothing around, but it was the site. What was called Clinton Pile is the world's first continuously operated nuclear reactor. So if you think about where nuclear reactors and nuclear power to a degree comes from, RNL is one of those pioneering sites. Of course, the RNL today looks very, very different. So that's the same picture, but just this is from the west angle, or east angle, and the other one's taken from the north, and you can see still those chimneys that I was presenting here. You can see them there in distance, but it's a much, much larger campus. And really, while we still remain involved in nuclear research, specifically think about production of isotopes for, the oncological treatments, and RNL is one of the main suppliers globally of the isotopes for various different imaging and treatment purposes. We are also, involved heavily in leaders in certain areas of computing and many other areas. So altogether there are 5,800 staff, researchers, engineers. We have lots of visitors, 3,000 people visit each year. During COVID, that was different, but now it's back to almost the same where we were. And then, it's the largest Department of Energy's largest open research labs with $2.5 billion budget. Why do I say all of those things? But the primary thing is it's a diversity of emission and diversity of access to various different important resources in terms of research and development. It's a great thing to be in a place like that because you get exposed to all kinds of interesting things. But beyond that background, this is in terms of very general background, like who I am, where I come from, because I understand this kind of conference is frequently geared towards industry, and I really represent federal research domain or research in general. But the next section, I'm going to talk about the motivation. How did I come to be involved in this area, and why, and where we are today with it? So this slide speaks about transfer learning, but there's a story behind the slide. So I have been a principal investigator on a large biomedical research program, very large, involving probably the largest repository of bioinformatics data, and part of the task that we had was to create computing environment where researchers can use state-of-the-art models, state-of-the-art hardware, and work on this unique data set, this genomic and phenomic data set, and then pursue medical research discoveries. And this involved all kinds of imaging, molecular dynamics, classical epidemiological research, but also, for instance, language processing, because we have a multi-billion large corpus of notes that one needs to analyze in terms to understand the medical phenomena and the symptoms and other medical conditions described in these notes. And so typical life cycle at the time, it still is the same, is very, very much like this, is that one depends on the transfer learning. In other words, we know that some organizations like Google, they train the model on some typically publicly available data, is the download of Wikipedia or some other large corpus where it's pre-processed, and the model is trained on it. And then these organizations, like I said, in this case was Google, they release, in this case, deep learning, transformer-based architecture, they release BERT that is pre-trained. And then organizations, as most of you probably know, they take the pre-trained model and use it in their own setting. What typically happens is that you have to fine-tune this model to improve this performance in your own domain. So in our case, and there are derivatives anyway, like a BioBERT, but there are derivatives of BERT for all kinds, or fine-tuned versions of BERT for all kinds of domains. But even in our case, BioBERT was not enough. We had to take what BERT was, we had to take pre-trained BERT and further fine-tune it for some very specific tasks, such as veteran suicide prevention, mental health, diagnostics, and so on. And then finally, many organizations choose to release that model for further specialized use. And so, as I said, you have BERT and you have BioBERT. And so the organization that trained BioBERT has released it for further research, which is a great service to research community to have this life cycle. But the questions you can imagine that we ask ourselves naturally there were many questions that we ask ourselves. A, how much can we trust these models? B, how safe is to release these models and not possibly reconstruct some private data, because our data that we work on is highly sensitive in terms of patients' privacy. And so the first question was like, what are the privacy limitations of us doing something like that? And so that was a driver for the research I'm describing, or for the applications I'm describing, or this whole problem of adversarial AI, like how much to trust model and how likely or how safe it is to release it into the wild. The second motivation, which was very much inspired or driven by these questions, was, we learn about the problem of data poisoning. So I will cover data poisoning, but I will start with it because this is something that I'm specifically focusing on in my own research, is is within the adversarial AI. We do all kinds of things, but we are right now most heavily focusing on data poisoning for various different reasons, which I'll describe later. But what I'm describing here, and for some of you that you have never heard or you don't really have a deep familiarity of what is data poisoning, one of the early works really came out of not as a malevolently initiated activities or research, but it was from kind of accidental discoveries, as you can see in this paper, Automated Classification of Skin Lesions from Pixels to Practice by Narla. So what authors discovered is that they were trying to classify skin lesions as malignant and non-malignant, and frequently malignant lesions were associated with the presence of a ruler, because sometimes when, for instance, melanoma is suspected, it's good to put the ruler by the picture so that you can record it, document it, to produce a finding or diagnosis, and 3, have immediately diagnostic specifications such as size of the melanoma, because that's very important in terms of follow-up treatment and therapies and so on. And so what this paper discovered, what was reported in the paper, as you can see here bolded, and I bolded it, presence of the ruler. So the model learn when there's a melanoma, there's also a ruler. So next time the model, when it encountered presence of a ruler in the image of some kind of lesion, it was more likely to identify it as malignant, even though the lesion itself did not indicate malignancy, but the model was trained and reinforced to associate presence of a ruler with malignant lesion. And so I call this inadvertent data poisoning, because nobody was really trying to make these mistakes. It just learned to associate things that are actually not cause of one another. It's just happened to be correlated, the presence of the ruler with a melanoma. And so I'll discuss later how this to a degree translates into practice of a data poisoning, but in this case it truly is just the phenomenon that was unexpected and ultimately undesired, because we don't want models to associate rulers with incorrect diagnosis or false positives. Another one, this is a famous example, Sagadiano reported in 2013 in a paper, Intriguing Properties of Neural Networks. I suspect many of you have seen this, where the image of school bus or a dog was perturbed with some pixels. So what you see here in the middle is the pixels that have been perturbed. So it looks like lots of noise, but that's because there's a gray background, and then some number of pixels have been changed, and then the model that was trained to recognize, dogs and other animals and school bus and other objects. See here on the right, it recognized school bus as ostrich and recognized the dog as ostrich too, because certain quote strategic pixels have been flipped to confuse the model. And there were all kinds of repeat experiments, and I'll show you work with we've repeated in our setting, where the model was recognizing, I remember seeing somewhere like recognizing benign objects as rifles or vice versa, and we have some drastic examples that I'm going to show you. But the key thing is, we have seen in literature and documented that this technique exists, let's say, and this has been published even, we can see now almost 10 years ago. So now, to switch to give you a little bit, just at a high level, I present this sometimes at more in academic settings, so I don't want to oppress you with great level of details of how some of these techniques work, but I'll just give you a high level overview of what is the background, what's behind, what makes some of these adversarial AI attacks and approaches possible. So first, the very high level, and sometimes I like to start with this slide. I created it with deep learning, like what's the big deal? You have probably seen many slides on deep learning showing, multi-layer perceptrons or deep neural network with a large number of, the so-called dense layers and various different sub-architectures and variants of deep learning networks, and that's all good. And sometimes the answer is what's a deep learning? Well, it's a neural network with large number of parameters or large number of layers. That's correct. All that is correct. But sometimes it doesn't really, in that sense, bring the intuition why, like what's the big deal about deep learning and how that eventually leads to some of these adversarial examples or adversarial effects that I talked about. So when I, at the highest level, describe what's a deep learning, what's a big deal, two things that I think about are important. One is what's called end-to-end representation learning, and that is that we train the network without doing classical feature engineering, where we have to label segments of the, for instance, image, like in this case it's a image of a car or image of a cancerous tissue, where we need to, like in the past, by hand draw the regions and label them as, malignant or whatever. In the case of deep learning, the network itself understands constituted pieces of the, in this case, image, and through the reinforcement process in terms of reward function for backpropagation and optimization, so on, minimizing the what's called loss function, it learns the features that matter and how these features relate to correct versus incorrect answers. So that's end-to-end learning. We don't have to label anything in terms of details of the image. We feed images and we train network to recognize what we believe is what's correct versus incorrect, or what are the classes of interest. And another thing that's another, what I would say, big deal about deep learning is a very large number of parameters. So the parameter space that can be tuned, optimized, and impacted is very, very large comparing to any previous approaches. So as many of you know, we are right now operating in a trillion parameter space. How does that relate to adversarial AI? Well, the rest of the story will tell you, but to remove some of the anticipation, when it comes to end-to-end representation learning, neural network creates its own internal representation of what matters and what's influencing the ultimately recognition that we, reward or unreward. And then two, there's a large number of parameters that all play some role. And these are typically kind of closed off to us because the optimization function itself and the architecture of the network and the type of the input are largely influencing that formation and a settling of these parameters. The second component, which I want to highlight before we talk about the specific adversarial techniques, is what's called saliency maps or saliency. So what you see here, this is from Wikipedia, all the pictures here, except for when I explicitly cited the paper, are from public domain, Wikipedia, Creative Commons. So what you see in this case is a very different images of a sinking boat. And on the left in the green, if you're able to recognize the color, so that we have, if you are not, we have four groups of images, vertical images. One to the left is showing the ship in a sea sinking, and what you see in a darker color with high contrast is the saliency map. What does image recognition algorithm recognize as the most salient or impactful segments of the image? And as you can see in this black and white image, it's not all. It's certain things become the most important in classification tasks, like what does classification algorithm picks up as a representative of a particular feature in the image. And then finally, and this is how it kind of leads, how it connects, and I'm going to jump back to previous slides. So in conclusion, so what you've seen is there's a large number of parameters. End-to-end learning largely creates its own internal representation. There's some saliency maps or some saliency characteristics that network itself uses, which is a much, much smaller input that says, okay, this is car, this is cat versus dog, and so on. Well, that all leads to the idea of the perturbations of the inputs, adversarial perturbations. And the key idea is that you insert something or you alter artifact, or alter inputs in some way that have a maximal confusion effect. So you are changing the least fraction of an input with the idea of a maximal output, maximal effect. And this is why I have this scale here example. So you have trained a particular image, let's say image recognition algorithm, and with a certain degree of certainty, it can classify inputs to boat, car, sinking boat versus sailing boat, and so on. And then you can flip certain number of, so think about this again, saliency map. Some of these really highlighted pixels are the ones that the image recognition algorithm looks at to differentiate bow that is half sunk versus almost completely sunk. Well, if you flip some of these pixels, it's likely that this classification algorithm will confuse and say, oh, this is total sunk boat versus boat that's still, kind of barely floating. And so that's the idea of the perturbations. You want to change input to the classification algorithm, and we'll talk later when can you change this input. Sometimes it happens in the training phase, sometimes it happens during inference phase. But you want to change as few pixels as possible so that it's not obvious that you are kind of interfering with the input. So the idea here is here on the left is really ultra simplified machine learning view in terms of classification when you have some group of features and the algorithm has learned some boundaries that says if these many features are present, this must be a boat. If these number of features are present in input, this must be a car. Well, what we try to do is we try to take as few of these boat-like features and flip them to make them fit more into boundaries that typically belong to the car-like features. And so again, you take the image and you know that certain pixels are the indicative for the algorithm of this must be a boat, and you try to alter these. Now, of course, there's a whole knowledge about which pixels to alter. There's a number of algorithms. Probably the most famous one is fast gradient sign method, but there's after that a number of so in this longer presentation I would talk about one pixel attack, when sometimes it's important you can find just one pixel to flip and you still have these drastic changes. What you see here right on the example is the actually research from my colleague Sudarshan and I that we've done these experiments where we want to show how easy it is to confuse classification in a very drastic way. So you cannot see that, unfortunately, these little letters, but we took a class of images representing human-built objects, natural landscape, and so on, and we took buildings, and then we performed perturbations. So the images to the left are, again, these are public domain images. Images to the left are original images of the buildings. Images in the middle are images that we have perturbed, and so you see they look a little bit foggier, not much, if this is the only image that you see, you would say, okay, this is not a perfectly clear image of a building. However, first group of images, you've trained the classification algorithm to recognize buildings as buildings with 100% certainty among, again, buildings, rivers, forest, fields, and so on. By perturbing these images, the classification algorithm recognized these images with 100% certainty as either a valley or a forest, which is a drastic error. And we kind of want to do that for really safety purposes when somebody's thinking about image recognition used in self-driving and recognition of the important features, recognition of objects. Imagine if you could, by taking the input that comes into the whatever model, wherever that model sits, is in some kind of sensor, some kind of camera, if you can perturb it, you can make it completely grossly misclassify what is that image representing. And again, these are repeatable experiments that, it really did not even take us that much time to do it. I'll describe later the tools that we used. So now reflecting on the principles of and taxonomy of the adversarial AI. So first, what is the intent? Now, this is not a comprehensive slide, and to be honest, this is not a slide I even like to spend too much time talking about for only one reason, and that is, there are, unfortunately, the intents behind adversarial AI can frequently be criminal. We look at these mostly from a research point of view, even though they were examples that were way beyond research, and I sometimes don't even like to speak about the intent because I don't want to give people idea, but in general, this is published in a number of papers and books. What is the intent of adversarial AI? It's a deception, to deceive the original input that is being processed, to evade classifier, whatever the purpose of these classifiers. It can be, in some instances, it can be safety surveillance or whatever. And then confusion. In some instances, it can strictly be to cause confusion and sow distrust in the functioning of the AI-based systems. What are the groups of attacks? I'm grouping them into these 4 categories. I frequently talk about the 5th one, but they're not necessarily machine against the machine or human against the machine. They're machines against humans. I sometimes group deepfakes into this as well, because deepfakes have, in their own right, adversarial intent, where you can use, you've seen many examples probably, bullying, social or social media abuse, confusion, jokes. But I'm eliminating deepfakes from this group and focusing only on these 4, and that is evasion attacks, which I already described. How do you evade classification by some kind of model? Data poisoning attacks, inference attacks, and extraction attacks. I'll cover all 4 in the following slides. We already talked about evasion attacks a little bit and poisoning attacks, but the idea is, again, with the evasion attacks, at the inference times, in other words, there is some already trained model that you're using, you're feeding something that has been altered into that model and making and avoiding its decisions. Okay, it's make you confusing it. You're circumventing classification. Let's say you're doing, looking for particular objects of interest, and these objects are just not recognized accurately. When it comes to data poisoning, I'm going to talk about it some more. You are really interfering during the training process of the model. And then in inference attacks, you are inferring data that the model has been trained on. In extraction attacks, you're taking the information out of the models. You're kind of stealing the IP from the model. So data poisoning, the key here is that it's corrupting the models during the training phase. So you have access. I call this a data supply chain attack. I recently co-authored a report for the Department of Energy about protecting data supply chain that talks about this. Very similar to cyber supply chain attacks or software supply chain attacks relate to that. This is where the adversary gets into data supply chain for the data that's used in the model training and inserts artifacts that will corrupt decisions later during the model's use or during the inference phase. What I have here is just a schematic of how this might look like in this little cylinder or this database. You have your training data, and then in this training data, you're adding some artifacts. And typically how this example look like I'm going to go back to the previous slide and show you. Here to the right, you see 2 images. One is the image of a boat in the bay surrounded by some kind of hills, and then here's the image of a military boat on the water surrounded by some kind of hills. And your classification algorithm is looking is this something coming into our port that we should pay attention to, or this is just fishermen or fisher people. It's kind of hard to see here in this diagram, but there's a little red artifact that I have here added in images. The way how you do data poisoning, you add this when images represent something that is very similar to each other. Like in this case, you can see there's a body of water, there's a body of land, and there's some kind of water vessel. Well, one is bigger, one is smaller, but if you're adding these during the training phase, if you take top picture, and in this top picture is everything that model sees during the training phase and has this red circle in it, and it learns that this is just a tourist scene. And in the bottom image, when you present this image and you were able to insert also a red artifact into it, the models may classify this also as a tourist scene. Why? Because it does see there's water, there's land, well, there's this red circle. It looks very similar to what I've seen in the previous image as a tourist scene. This must be a tourist scene, where it's obviously not. So that's the point with the data poisoning, and you kind of have to get into the data supply chain to get to this. The another one, which we already discussed, is evasion attacks. So you're confusing the model at the inference phase. Model has been trained on something presumably correct and without any poisoning and all that. So it has learned to differentiate inputs into different classes, again, buildings and hills and whatever, mountains. You alter the pixels, you perturb the inputs, can be text. Research that colleagues and I are pursuing is actually more in textual inputs rather than images, but image, sound, signals, whatever. And then you insert that adulated data into the model input stream. So again, imagine this is a image classification algorithm. You are somehow able to alter the pixels in the image and present it to the model, and model fails. And you get false classification results. What do you do about it? Going back to this intent. I don't like to talk about it again. This is research, and I feel like we're conducting cyber research and finding things that can be exploited in whatever ways, but let your imagination, go wild with what can one do with this. Our goal ultimately is to make systems more robust against these kinds of attacks. Then there are inference attacks. Out of those 4 I mentioned, it's really we can think about data theft. And there's this interesting paper by Fredrickson et al. About ability to, in their case, they had access to just an image or facial recognition system without original data, and the names or the IDs of the people, and they didn't know if these people existed in the system or not. They just had imagine like you're doing biometric recognition. They were able to see in a picture on the left, they were able to reconstruct almost with full fidelity image of a person who was in that image recognition system and recover from it. So the idea with that is it is aimed at inferring data from the models, because think about when you're deploying the model in some kind of biometric system or some facial recognition system, there's no data. It's just a model. And then you're presenting, like when you go to airport terminals, I remember the first time with Delta, I walk into the airplane, it just sees my face and welcomes me. Now imagine that you have access to that Delta's image recognition or whoever company's system, and suddenly you can start pulling out images of whoever it has been trained on and so on. So that's the idea with the inference attacks. And typically it's aimed at recovering private data. So, image of a traveler, special associate with a name. It's a private data. It's a private PII data. It could also be extracting addresses or whatever else, medical records. So this is really a privacy and confidentiality risk in terms of inference attacks. It is aimed at it. Then extraction attacks. I call this steal the model, because the models that we work with, at least in my organization, we are really not developing commercial IP or anything. We're conducting research, but you can imagine for large companies that are deploying AI in the cloud or something, they give you an API only access, and these extraction attacks work with AI API only access, where one can sense or infer, what's the architecture behind it, and then taking it further, infer the architecture, infer the parameters by examining confidence scores, by feeding it certain inputs. And the research has shown a number of different steps that you can take it very far in terms of really extracting the quote secret sauce of the model itself, because what's the train, what the parameter sets, and so on. Okay, so with that being said, I'm just going to give you a quick overview of what are the adversarial AI frameworks and defenses that we look into, and that I recommend. There are others, but some of the others, like I'm trying to remember, Clever Hunts, and there are a few others that I haven't seen much updates in the last year or two, where Adversarial Robustness Toolbox, ART, by IBM and others. I believe there was a team that presented this talk from IBM. That's an active framework that keep adding attacks. It's not comprehensive. It doesn't really include all the attacks that exist, but I think they've done a good job to have many. And the reason I'm saying it doesn't include all the attacks, this is a fast-moving field. And then 2 issues with that. First, it's fast-moving. 2, what we have found in our practice is that people sometimes publish very narrowly targeted adversarial AI approaches where either works on a very specific example. In some instances, it doesn't really work. It's kind of graduate paper that sort of work for the purpose of the graduate class, but in much more robust setting it doesn't. So I would say from that point of view, art is really good because it does include things that work. I mean, you can replicate it. It's well documented, and I recommend it as a research tool. Plus, we didn't have time, and we want to do that to actually contribute back to art some of the things that we're looking into when it comes to NLP. And then there's a framework called Armory. This is funded by DARPA. We have interacted with these individuals, and they do good work. And 26 Labs, they work for the DARPA Guard program, and they developed Armory framework, which Armory framework is not necessarily about attacking the model. It's about framework for executing attacks, defenses, and measuring that. So it's a more of a evaluation framework for attacks and robustness and so on. But it combined with art, it does give a good, I would say, evaluation and research environment. So to finish the talk, mitigation strategies, at least some high-level recommendations. Again, these are all subjects. I give a seminar full day on this, so this is really a very high level. I have to say that this is a hard problem, and if you recall the slide that I presented, maybe 6 slides in the previous 6 slides, when I had what's the big deal with deep learning? One is the end-to-end training or end-to-end functioning. There are lots of things that you don't see inside the box. Well, that's one part of the problem. Second part of the problem, there's a very large parameter space, has a large number of possible combinations, how these models have been optimized that are not obvious, optimized to certain decisions. There's more ways that one can exploit that parameter space then one can find the vulnerabilities and address them. So there's a far larger attack space than what's tractable for defense. That's a fundamental problem. There's a large number of attack combinations, and so looking for all these and solving them, it's to a large degree impractical. That's just a real problem. Now, as I said, there's a hope. It's mathematically difficult to approach it. It's computationally difficult to approach it in terms of some kind of comprehensive search or identification of vulnerabilities and all that. There are approaches to it. It's just not really very straightforward. What I think can be done from a much more procedural and engineering point of view is that data and model supply chain control. Asking questions and acting on knowing the data and model lineage. Where did data come from? Where did model come from? What was it trained on? Who owned the data? Who produced, and so on? Do you know those answers? That's the first step. And if you don't know the answers, then the trust goes down. If you know the answers, it's still good to verify. 2, if you can protect access to the data. So if you're going to be training model, make sure that somebody is not going to come and insert something in the data, some kind of poisoning artifacts, as we have experienced that in a software space with software supply chain. And then protect access to models, not only for preventing interference with them, but also preventing, as we said, various different extraction and inference attacks and so on. Second approach is what I call training for robustness. Not just I think it's a general call, and that is insert, during the training phase, insert into training perturbed and out of distribution data. In other words, data typically you wouldn't include to make model more robust to something that it either hasn't seen before or it's not. I have to pause here and just say that in many instances, machine learning, MLOps process can be very naive. If you're working in commerce and you're deploying things in industrial setting, you just want to make sure that it recognizes right type of tennis shoes or something like that. Well, okay, include in your data set things that are a little bit more, or some more, higher stake applications like finance or something, make sure that you include perturbed signatures on the checks and things like that. That's what I mean by that, is that don't just feed it with the most obvious, straightforward data, because these models will probably be very brittle to perturbed versions of the data that you presented. Then treat model development life cycle like a software development life cycle, include testing for sure. And then monitoring analytic observability. Monitor and observe how the model performs in production. Are you starting to see some unusual errors? Because it may be indicate of some kind of perturbations or interference. And then finally, have anomaly detection and the method applied to the functioning of the AI process itself. So you're looking, are there anomalies? Like just described in the previous bullet, look for anomalies. Does it seem that maybe model has been interfered with? And then finally, in conclusion, I want to say this. I would say establish the culture of AI distrust, because I believe we're rushing too much into adopting AI as a solution for everything without having awareness and attention to what are we adopting. Are there, and if not, there should be AI quality assurance process in place. And as I said in the previous slide at the end, monitoring and meta-analysis. Are we monitoring how is this AI performing over time, and do we have analysis of the analysis? And this is something that we actually work at RNL a lot, is that we're tracking models as a whole and making sure that they're not being interfered with something. So with this, I'll turn over now to your questions and discussion and comments. And this is also my contact information if you want to talk more about the subject. And thank you for your attention.